Okay, good morning, everyone. So first of all, I would like to make some of the revise for the Venn diagram I showed in the last week. So this should be this page. In the case of to form the Schottky contact, where our work function of the metal larger than phi s, and in this case should be the metal on top of the N-type semiconductor. And then in this case, once the metal on contact with our semiconductor, we will be able to form the Schottky contact. So last week we showed this in the p-type, which is not correct, because in the case of the phi n is larger than phi s, and in the case of the metal on p-type, that will form the ohmic contact, which is also shown in the slide later. So today we will continue to finish the rest of discussion related to the metal and semiconductor. So we have shown in last time that in the case, that's where I mentioned that in the case that we have the metal and p-type semiconductor, and in the case of the metal work function is larger than semiconductor work function, and in this case that we are able to form the ohmic contact between the metal and semiconductor. So there's one special case that we call as a tunneling barrier. This tunneling barrier is considered that if the space charge width in a rectified metal semiconductor contact, as we know that the space charge width is inversely proportional to the square root of the semiconductor doping. So this sentence means that once we increase our doping concentration in our metal and semiconductor junction, and then we can expect that our depletion width is reduced. And in this case, the width of depletion region decrease as the doping concentration in the semiconductor increase, and therefore, as the doping concentration increase, the probability of a tunneling through the barrier increase. So this is a region where this sentence mentioned that the probability of the tunneling increase. So therefore, we call this as a tunneling barrier. This is very useful in the case that once we want to reduce the contact resistance. So in the real consideration of our device, where we will make as you know that in the source and drain region we will have the doping, and on top of the doping we will have the metal, so we have the metal on top of the source drain doping region, and then we all knew that we have to consider the contact resistance in between the metal and semiconductor junction. So in this case, if we can make this as a N++, in the doping source and drain region. And in this case, we actually N++, that means that the doping concentration is increased. And then the purpose to make the higher doping concentration in this junction, in the end, the purpose is want to reduce our contact resistance. So this is exactly that why we mentioned the tunneling barrier here, because in the end, that the purpose is that we hope to form the tunneling barrier between the metal and then semiconductor. And once we have tunneling barrier, we can further reduce the contact resistance. So this is a theory behind that why we increase the doping concentration. So in this case, we can have the tunneling barrier. And then with help from this tunneling barrier, we can further reduce the contact resistance. Also, we can try to calculate the contact resistance, especially that as we discussed before, that the purpose to form the metal semiconductor is either to form the good Schottky contact, that we need to have the good Schottky contact, Schottky rectified characteristic, or we want to make the lower ohmic contact resistance as possible as we can. And therefore, the determining of the contact resistance is definitely very crucial. And here we won't show the calculation, but just show in the end, our contact resistance is proportional to this term. Especially, we can see the contact resistance is correlate with the Schottky barrier height, and also is correlate with our barrier height, and also correlate with our doping concentration. So now, with this analytical equation, we can understand as long as our barrier height reduce or our doping concentration increase, and in this case, we can always try to have a lower contact resistance as possible as we can. So from theory point of view, already mentioned in the previous lecture that how this barrier height could influence our carrier transport. And also in the last slide, we also mentioned that how this concentration will influence our contact resistance. But now we also have this analytical equation to prove that our contact resistance is direct correlation with our barrier height and doping concentration as well. Okay, so next one I want to show you a literature that also discuss with Schottky barrier height on contact resistance. As you probably will expect that the Schottky barrier height or the contact resistance is not that important for the nowadays semiconductor, but it is not true, especially in the lots of advanced semiconductor material. We are still faced to get a good Schottky barrier, or we still face a challenge to get a good contact resistance. So this is a literature published in the 1996, and then as you see from the title, it says that this is paper discussed with the Schottky barrier and contact resistance on P-type gallium nitride. So then again, if we look at the abstract of this literature, so this is abstract. So we can see that the first sentence follow the same format that where we mentioned in the last, when we go through similar literature, we have mentioned that the first sentence just a general summary. So the first sentence mentioned that we measure Schottky barrier height and specific contact resistance of 4 different metal on P-type gallium nitride. So in the first sentence, just a short conclusion, the short introduction of what would be the purpose of this work. And also in this paper, they discuss 4 different metal: PT, nickel, gold, and titanium. So the Schottky barrier height of these 4 metals were obtained from the current voltage characteristic, and where they get this value, different electron volts, and also the specific contact resistance will measure as well. So this actually just try to be consistent with the title, because as your title already mentioned that this is paper going to discuss with the Schottky barrier and contact resistance. So therefore we expect that in the abstract we should also mention certainly with information related to our Schottky barrier and also related to our contact resistance as well. So this is one very coherent way to write the abstract, that basically we just try to make sure that the text in the abstract can be consistent with our title. And the next one is try to point out that the certain try to point out the certain experimental result. So the result proves that the Schottky barrier height and specific contact resistance decrease with increased metal work function as expected theoretically. So you can see this is a paper published in the Applied Physics Later, which is one of the very well known and very good journal, which is Applied Physics Later. And then you can see that what this author try to do is that they try to measure the 4 different Schottky barrier height and contact resistance on the 4 different metal. In the end, the conclusion just shows that the results are consistent with the series. And what is series? The series is the series in the semiconductor textbook. The series is based on silicon. So this means that this is a series that actually similar to the case that where we discussed. So in the end, you can realize the structure of this paper is very simple, and then the experimental results are very simple as well, because in the end, they just want to prove that the idea of these different metal on P-type gallium nitride are the same like the case of a silicon. So this is abstract, and then if we go to the conclusion, so we can figure out that the conclusion actually is trying to say the same things. So in conclusion, we measure Schottky barrier height of 4 different metal on P-type gallium nitride. So now you can see this is exactly the sentence as the first sentence in the abstract as well. What they are trying to say are exactly the same things. Of course, they provide some more detail by using the both larger area content, reverse bias IV characteristic. And we also measure the specific contact resistance. And the conclusions here, it was found that the Schottky barrier height and specific contact resistance decrease with increase of metal work function. So then again, the sentence illustrate here are exactly the same mentioned in the abstract. So in the end, the conclusion just another reflection of abstract, and then abstract just another reflection of our title. So everything is very coherent with a case for the academic writing, that we want to make sure that the main point illustrated in the abstract in the end is also summarize the same things in the conclusion. So basically, if you know how to write the abstract, and then the conclusion just refresh the sentence in the abstract. And also, there's some more details here. The Schottky barrier height are slightly affected by metal work function. That's just some small additional things mentioned, added in the conclusion. So this is abstract, and this is a conclusion of this journal. And if you look at for this, the right hand side is the introduction part. So introduction, of course, in the few paragraph of the introduction, from here to here, I won't go into the detail, but if you look inside the detail, you will find out that this just background information to mention that why we still need to spend the efforts on Schottky contact, Schottky barrier and contact resistance of the P-GaN, P-type gallium nitride. So this just correlate with the background information to explain that nowadays the P-type gallium nitride, we still need to spend the effort to understand the Schottky barrier in the P-type gallium nitride. And then there's one particular important keyword is recently. So recently also mentioned that this is there are some recent progress that we need to be careful. That's why that after this recent progress, we have to put more efforts to understand. So the recent progress is that the P-type gallium nitride has been achieved by magnesium dope. So that's a recent progress happened in around the 1990s. So after this recent progress, we still need to put more efforts to further validate or further try to demonstrate something on this recent progress here. And then another key words here, usually we will very often use for the academic writing in this. On the other hand, so this is the words has the same meaning of however. So normally, when we see the keywords of on the other hand or however, that means that after this keyword, we will start to talk about the motivation. So then, the measurement of Schottky barrier height or P-type gallium nitride contact is difficult due to a low resistance ohmic contact. It requires a conventional current voltage method. So that's our motivation for this work. So this sentence just try to explain that based on the recent progress is finally we develop a way to achieve the P-type gallium nitride. But now the new challenge is that it's very difficult to measure the Schottky barrier height. And also, this becomes one of the major challenges to clarify the electrical property of a p-type gallium nitride. So now we have the motivation. So after the motivation, finally, we will illustrate the main goal for this work. So there's a key word here. In this work, so in this work, finally, we explain how should we do to address, to fit this motivation is we systematically measure the Schottky barrier height of 4 different metal on p-type gallium nitride, and using the IV method, which utilize the large area content and reverse bias IV characteristic. Finally, we mention our methodology in here. We mention our approach. So this is our approach. The approach in this work. So in the end, that finally we finish the introduction part. We let the author to understand that what actually the approach we will use in the end to understand the Schottky barrier and contact resistance on p-type gallium nitride. So now, if you don't look any IV characteristic, you don't look at any experimental result. So far, we didn't look at any electrical curve yet. We just look at some keyword and try to understand the abstract, the conclusion, and also the some part of introduction. I guess you already understand the goal of this work. So the goal of this work is very simple. Just try to measure the 4 different metal on top p-type gallium nitride and try to extrapolate the Schottky barrier height and contact resistance. So this is exactly the same things that in these lectures we talk about. In the beginning of this metal semiconductor, we also try to understand the Schottky barrier, and in the end we also try to calculate the contact resistance. So for sure, we still show some basic characteristics. So then we have this very normal IV curve, and then from this IV curve we can extrapolate the Schottky barrier height. So if you try to look at this IV curve in detail, you will find out that this is exactly the same IV curve that we already mentioned. Okay, so that's all. So we finished for the metal semiconductor. Then we'll move on to the next one. So the next one, we will start to talk about the fundamental of the MOSFET, where is metal oxide semiconductor field effect transistor. So finally, we move to the case that we are most interested in. So we spend the more than 60%, 70% of the time in this class is we try to build up the fundamentals that can help to understand the MOSFET transistor. And finally, we will combine all these fundamentals together, and then we all apply these fundamentals together that can help to understand the typical operation basis for the MOSFET. So the first one is at the heart of the MOSFET. If you look at the critical part of the MOSFET is MOS capacitance. So the typical structure for the capacitance is shown here. It's very simple. It's the same region like the gate region in the MOSFET, where we have the silicon substrate, we have the silicon dioxide SiO2 with the dilution constant of the exon oxide, and then we have the gate metal. So this is a very simple MOS capacitance. And then there are the two critical parameters that we should be aware of. One is dielectric constant. Another one is our oxide thickness. Because these two parameters in the end will determine the capacitance value. The capacitance value can be calculated by the X zone over the distance. In our case of the MOS capacitance, this will be equal to our oxide thickness and also our X zone X0 here. So that's a very simple calculation for our oxide capacitance. So now you can understand the decrease of oxide thickness. So either we make oxide thickness as a smaller, or we increase our dielectric constant, then we can have the higher capacitance value here. And then the higher capacitance value is very important because later on we will talk about our current, the drain current. If we have followed the electronics, the basic electronics in the undergraduate, you should be able to understand that the current equation should be somehow proportional to our mobility and somehow proportional to our capacitance and somehow proportional to our Vg minus Vth. So that's the saturation, the current equation in the saturation region, where we will explain later. But now, if we can try to make our capacitance larger, then we can have a higher output current. And in general, we can consider the higher output current that makes sure our electronic device has a higher performance. But before we go to the real part of the MOSFET, first we will spend the effort to understand the MOS capacitance, because of the fundamental, the critical part for MOSFET still rely on the MOS capacitance. So if we understand the MOS capacitance, that will highly help us to understand the MOSFET later. So first of all, we need to understand the band diagram inside the MOS capacitance. So imagine we have the region that has a top metal and then the bottom metal. The reason that why we can consider this case is because of similar to this one, is that we were going to apply the bias somehow in here, and then we normally put this as a ground. So then the purpose for this dielectric is going to separate the charge from the top and then the bottom. So we have the charge being separate from the top and bottom. So then we can consider this as a case in this line where in between we have a silicon dioxide with a distance of a d and with our dielectric constant of X0. And then in the case where we apply a negative gate bias on top, which means that we will connect our bias in this region where the bottom is we apply the positive, and then the top is a negative Then, if we consider in this case, and that means the electrode in the bottom has a positive charge, and then the electrode on the top has a negative charge. And with this charge distribution, we will have the electric field from the bottom to the top as well. So this is a case that actually we would like to discuss. And in this case, if we imagine this is a situation where we have the P-type semiconductor, and on top of P-type we have a one dielectric here, and also on top of the we have the metal electrodes. So the left hand case is exactly in the right hand case where we apply the positive and negative, and where the positive is connected with the P-type substrate, and then the negative is connected with the top metal. And then in this case, because we apply the bottom as a positive bias, and then the positive bias will try to push the holes toward the top, and also because we apply the negative bias here, and as we already shown, the electric field is in this direction. So in the end, we can consider there's a negative bias here, and then the holes will be pushed on top. But in this case, we consider our dielectric is perfect, so the hole cannot tunnel through the top, and therefore the hole will be somehow start to accumulate below the dielectric, and therefore we can expect under this condition with a P-type with a dielectric with a metal, then we can expect that the holes will be accumulate below our gate dielectric. So we will have the holes accumulation. So then the top figure will become the one showing on the bottom figure. So that's why that with the bias of the negative on the top electrodes, then we can expect there will be the accumulation of the holes at the oxide semiconductor junction corresponding to the positive charge on the bottom plate of the MOS capacitance, and then the electric field can be calculated by as a voltage divided by the distance. So that's the first state, because what we are interested in is that as these are the two terminal devices, so therefore we will for sure interested to the first one. We apply negative gate bias on top, and we start to switch from negative to the 0 and 0 to the positive. So now we are in the beginning. We are applying negative gate bias on the top, and then we will have the whole accumulations under the gate dielectric. So in this case, we call the accumulation region. So now the next phase is that first we apply negative gate bias, but now we will be interested in is what happens if we apply the positive bias. So in the case of the positive bias, then we will have the P substrate and dielectric and also the gate metal here. But as I say, now we change the bias condition where we apply the positive on top and negative on the bottom, which we have the positive and negative here. So we apply the positive on top. So now we can foresee that once we apply the positive on top, that means we will force the holes try to far away from the interface, right? Because that's due to the Coulomb repulsive force. Where we apply the positive on top, will force the holes will leave away from our interface. So the holes will be moving away from our interface, and then the negative electrons can be appear at the interface. So this can be understood by two ways. One is you force the hole go away from interface, or you try to attract electrons close to interface. In anyhow, we will start to see under the bias of the positive on top, we can foresee the electrons accumulations in the interface as well. So this is the schematic as shown on the right. And because right now we try to induce a certain negative charge, so in this case we are able to induce a space charge region on this interface. So if the electric field penetrates the semiconductor, in this case, majority carrier holes will experience a force away from the oxide semiconductor interface, because now we are consider the situation in the P subs where the holes are the majority carrier, and the majority carrier hole will be experience a force try to away from our interface. And as the holes are pushed away from interface, then a negative space charge region is created because of a fixed ionized acceptor atoms. The negative charge in the induced diffusion region corresponding to the negative charge on the bottom plate of the MOS capacitance. So in anyhow, once these holes being pushed away, then this negative charge appears at this interface, and then that will work as a bottom plate for this MOS capacitance. So the text sometimes is confusing, but if you try to follow my way to think about all the charge formation, in the end it should be much easier to be understood than how this text mentioned. Okay, so now we move to the case that in the end we will want to use a Venn diagram to try to systematically to understand the case under the negative or positive bias. So the first one is that we would like to introduce, in the case of the MOS structure, with considering the, for sure in the substrate we have the EC, EV, but now we consider the P-type substrate where our EF is close to our valence band, and then we have our silicon dioxide, and on top of silicon dioxide we have the gate metal. There's one particular condition that our gate Fermi energy for our gate is aligned with our metal, our Fermi level in the semiconductor, and this is a case where we call as a flat band condition. So the flat band condition means that the energy band is flat in the band diagram in the whole system. And as we know, if there's no any band bending, if the band is flat, that means indicating that no charge exists in the semiconductor. So that's the first case that if, of course, it's very difficult. In the later on, we will talk about that there's one specific condition to reach in order to make the flat band. But in reality, if you just put the metal on top of the semiconductor, even without bias, due to the metal work function is not the same like the semiconductor work function. So in reality, without zero bias, you won't get the flat band condition. There's one particular case we will talk about later. But now we move on. As we say, the goal is try to understand the case with positive and negative voltage applied on top of the gate. So what happens if we apply the negative voltage? So if we have the negative voltage applied, so the negative voltage applied will cause a slightly band bending in our semiconductor. But in the case with silicon, still the same, where EC, EV, and our EF is still here. But now, because we apply the negative gate bias, the negative gate bias, that means actually our Fermi energy for the metal will lift up. So therefore, the Fermi level for the metal and Fermi level in semiconductor is not the same anymore. This will lift up, and once lift up, this will create the band bending in the MOS. This will create the band bending in this oxide dielectric. And also, not only the band bending in our silicon dioxide, but also the band bending inside our silicon semiconductor interface. So we will start to see the band bending in our dielectric, but also the band bending in our silicon interface. But now you will see at this region, our EF is close to our EV. Then once our EF close to our EV, that means the whole concentration here is increased, right? So that's what we already learned from the beginning of in the middle of this class, talk about that once our EF is close to EV, then this will start to become like more kind of P-type semiconductor because we have high holes here. So this actually also suggests we start to see the hole accumulation. So now everything is very consistent. No matter we use a band diagram or not, everything can be explained. But now with the band diagram, that will be useful because later we can use this band diagram to do more analysis. And again, another case where we are interested in is we apply the positive voltage. So similarly, we have EC, EV, and EF. But now, because we apply the positive gate bias, so therefore, we will start to see our metal work function will lift down, will below our semiconductor Fermi energy. So this will cause the band bending in our silicon dioxide and also the band bending in our silicon in the silicon interface as well. So now we can foresee, so try to be more precisely for explanation. So I slightly modify the EF. So now the EF is here. But now we can see the EC is getting close to our EF. So that suggests that this will induce the negative space charge. And this is our depletion width. But still, although it's close, but it haven't completely like the EF is larger than EC yet. But the EF still below EC, but it's already slightly to change the charge from the positive to negative because now our EF is close to our EC. So finally, in the last case, we are interested in how about if we apply a very large positive gate bias. So by applying the sufficient large positive gate bias, this also will change the band diagram as well. So again, we have the EC, EV, and where our EF is here. And because now we apply a large gate bias, for example, like here, so this will create, this is a larger so this will create a huge band bending as well. And the huge band bending not only happen in our dielectric, but also in our semiconductor interface. Therefore, it is possible that our Fermi energy, our conduction band in the semiconductor can be below our Fermi energy in the semiconductor. So in this case, now we can see this is a region of Fermi energy is larger than conduction band. That means right now this region become the pretty high concentration N region, and in this case we will induce a lot of electrons here, and this is sometimes we call the inversion layer. So by applying a sufficient large positive VG, we have inverted the service semiconductor from P-type to an N-type. So now this is not actually the N-type, it's N++ type in this service. Then we have created an inversion layer of electron at the oxide semiconductor interface. So that's the case where we apply the large positive bias. Okay, so similarly, we can draw the same band diagram analysis on top of the N-type semiconductor. And in this case, with the N-type semiconductor, we have the Fermi energy close to our conduction band. So in this case, the bias condition for the accumulation, inversion, or the huge electron inversion just completely opposite compared to the p-type. So in this case, we need to apply the positive voltage to have the accumulation of electrons. So that's for the accumulations. And then we apply a small negative voltage that start to induce the positive space charge region. So this is our space charge region. And then the last one is we will apply the large negative electron. So in this case, we produce the inversion of the holes. So this is the case of the N-type semiconductor. So just a opposite operation compared to the p-type semiconductor, but the operation principles are the same. So now we move to some analytical calculation, but this equation we just borrow from the previous lecture, but we just put some consideration in our case. So the first one is that we will be interested in this depletion layer thickness, which is this one. This is in the case of the p-type substrate, and then we apply the small Vg, and that will induce a space charge region. And also we have the one term here, it's called phi s, where this is a surface potential. So now the phi fp here can be calculated as a phi fp is equal to Vt natural log Na over Ni. So, and then the potential phi s here is called the surface potential. And then the space charge width now can be written in a form same as a one-sided p-n junction, where our xd is equal to 2 exon phi s ENA. So we borrow the equation we already have from the one-sided p-n junction, and we just put here. And now we are moving on to consider one particular case, that if our phi s is equal to 2 phi fp, And this condition is known as a threshold inversion point. And then also the gate voltage applied to induce this condition is known as the threshold voltage. Which we already mentioned previously that in the case of a MOSFET, the most critical characteristic is the IDVG, and in the case of IDVG, as once our gate voltage applied larger than certain point, we start to see the current increase, and we define this as a VTH, which is this one. So now we will try to understand that why in this region we start to have the current increase, and then how do we determine the threshold voltage here? The electron concentration at the surface is an exponential function of the surface potential, which our NS is certainly exponential, proportional to our exponential phi s. The surface potential might increase by a few kV, which will change the electron concentration by order of magnitude, but the space charge width change only slightly. So that means we apply a small increase of gate voltage, then the electron concentration here will change dramatically, but the depletion width doesn't change a lot. In this case, the space charge region has essentially reached a maximum width. As shown me here, this is a maximum width. In the case where our phi s is equal to 2 phi fp, and then beyond this condition, the slightly increase of gate voltage will induce the dramatically increase of the electron concentration in the surface, and this start to generate the electrons in the channel where we have the source, drain, and gate. So this high concentration electron in the surface, in the end, is the same as a high inverted electrons in the channel when our VG is larger than VTH. So the analysis of this two-terminal MOS structure in the end is going to help us to understand the MOSFET. So we should always time to time to correlate the electrical result in the MOSFET compared to the analysis in the MOS capacitance. So similarly, we can make the same analysis on an N-type substrate where our phi s is equal to 2e phi fn. Then also our phi fn is equal to nd ni. And then in this case, the EF is actually close to our EV. So in this case, now the EF is much close to our EV. So we start to have the whole inverted here. So this is very critical, because in the previous slide we talk about the IDVG, but we only talk about in the P-type substrate where we apply the parity gate bias beyond the threshold voltage. We have the current flow. So this is our threshold voltage, and the reason why we have the current here is these are the electron inversion in P substrate, and because of these are the electron in the channel, so we also call this as an N-channel MOSFET. NMOS. But with considering the N-type, we have the same characteristic. Once we apply the negative bias enough, then we start to see the current increase, where we have the whole inversion in N substrate, and because we have the lots of the holes in the channel, so we call this as a P-channel MOSFET, or we just call this as a PMOS here. So the purpose to develop the NMOS and PMOS at the same time is because of there's one particular circuit where we have the on top we have the PMOS, on the bottom we have the NMOS, and then we connect it together with one input and one output. So this is very important for our logic circuit. This simple structure is we call as an inverter, and then the combination with P and N is sometimes we just call this as a CMOS. And the purpose for this inverter is that if we apply the input signal as a 0, then we produce the output signal as a 1. And if we apply the input signal as a 1, then we have the output as a 0. So then we can have the invert of our digital signal from 0 to 1 or 1 to 0. So that's very important for our logic circuit. So that's why in the end the development of the N and P modes are very crucial. Okay, to move on. So, as we already mentioned that our NS, our electron concentration, is proportional to the certain exponential. So therefore, we will be interested to understand the surface charge density, where our N is equal to Ni exponential. This is some old equation that we already mentioned. EF minus EFI over KT. But now, if we consider that this also the NS can be also expressed by this one, because the EF minus EFI is equal to this phi FP. But now if we apply the additional gate bias, so additional gate bias will cause this delta phi s. So the delta phi s is due to apply bias. So now we can rewrite the equation as here. So this equation will become this one, and we consider the previous one is NST. Then the NS is equal to NST exponential delta Vs over Vt. So this is very important, because this suggests that actually the delta Vs, if we increase our delta phi s to have additional 60 millivolt, then our NS will 10 times larger. So as you can see from this graph as well, this is 25P. This is 25P plus 0.06, which is 60 millivolt here. So additional increase of the 60 millivolt in phi s, that can cause the 10 times increase of our surface charge density. So this delta phi s 60 millivolt, and in the end will cause our NS 10 times larger. So in the end, this implies, if you look at this, this is a graph with NS versus phi s, but in the end, this will have the same result in the case of our current versus voltage, where ID, VG, and then if we put it in log scale, then we will get the same result, that the increase of the 60 millivolt in the gate voltage this delta VG 60 millivolt will cause current increase 10 times here. So then if you try to calculate the slope here, the slope is actually how we call as a subthreshold swing. Or we call as a subthreshold slope, SS. So ideally, without any non-ideal factor, the best slope we can achieve, the lowest slope we can achieve should be 60 millivolt per decade. So the inversion charge density increased by a factor of 10 with 60 millivolt increase. Of fires. So this information is become very crucial because now if you have already worked on some of the transistor, it's really care about the substrate swing or substrate slope, then you probably will notice that everyone talk about the bottleneck, the lowest SS can be ideally achieved is a 60 millivolt per decade. We cannot, ideally we are not able to achieve below 60 millivolt per decade. And why the 60 millivolt per decade? This number, where this number is coming from, is actually coming from this slide. That's why we have the theoretical estimate that the additional 60 millivolt gate bias can cause the 10 times increase of a current. So then most of the advanced transistor nowadays just try to lower the SS to be similar to the 60 millivolt per decade as possible as we can. So this is some of the work function difference in the two-terminal MOS structure. And then in the left-hand side is the energy level in the MOS system before the contact. So this is a similar band diagram to the metal semiconductor, but now we change to the metal oxide semiconductor. So we have a metal work function, we have a semiconductor here, we have the dielectric here. So now you can see once we put together, for sure that this is a case that in the thermal equilibrium after the contact, then we can see that there will be the certain band bending in the dielectric as well. And this is because due to the phi m and phi s here are not the same. So that's why we can foresee there's a band bending inside the oxide here. So in the later, we will start to try to analyze this work function difference. What would be the cause of this work function difference in the two-terminal MOS structure? So then we will take a short break for 10 minutes. So today, you need to hang in the homework. And also as mentioned in the TA from the mail that if you bring the homework 3, because there's a mistakenly grading in the homework 3. So you should bring the homework 3 in the meantime, and then we will do the regrading again.
上次功课
礼拜homework 3。如果是年薪100，是不是？
对。
哦，你有100就不用交回来。对。
3份作业没问题的就不用。
哦，不用，对对对。
Bring the homework 3 like later because I thought it was optional.
If you're how will be your score for this one? If you are 100%, then you don't have to read. Yeah, it's only for the there's some slightly mistake for the grading the one question. Yeah. So if you are 100, you don't have to read. Yeah.是。
我想问那个 TSI 课程的，就是它有收据要现在要交。
OK 啊，你可以先拿出来。你有上没有交大统编吗？你有开交大统编吗？我看一下。
可以问一下，刚刚讲到这个 delta bias，
对，
这个好像没有在上面画出来。
它这个只是解释说它的 additional 的 bias 的话，它会 cause 多少你觉得 bias 就是一个这个gate bias 造成的不同的 service potential 嘛，所以你把 bias 突然再增加2phi加 delta bias， 它最后对我们的 NS 会影响多少？你这样了解。它主要是表达的，今天你不用看这个，它主要是表达说，光从这个 equation 上面看到，如果你多了一个60 millivolt 或多少 bias， 它对你的 NS 影响多少？
哦，就先不要管。
对，那只是说，你就是 bias 就多个 bias， 你就是在 band 跟下 band bending。对，就这样子。
哦，
对。
那它只讲这样。
对。 Okay, so before we continue, let's talk about the update schedule. So in the last time we mentioned there would be the mega class. So original was arranged on it should be on this Thursday, but unfortunately I cannot find any classroom available on this Thursday, so I decided to rearrange on the Wednesday. So we will start the 6:30, and then the classroom is ED 116. So on this Wednesday afternoon, and of course that you feel free to join if you cannot make it. Anyhow, I will record it and then upload in the YouTube later. But of course, if you still want to join, that I will be here on the Wednesday evening. And I also propose that they could be also needed for some additional mega, because I'm not sure that I can finish the targeting progress. So that's why I still hope that this can be the one option for the additional mega class. That would be in the May 28th, still will be the same Wednesday afternoon. So with this mega class, I think for sure that we are still be able to have the exam on this day. And then also one more thing is that because on Thursday the classroom for this is not available, so that would be the next one, just next to this one. So that would be the ED 219. So I will make the reminder once we approach to the final exam. Okay, so back to the class. So now we would like to start to understand the impact of work function difference between the metal and then semiconductor, and what would be the issues here. So we can see that with this consideration, now we have several different terms. Is phi n is a modified work function. Original is E phi n, but now we have a phi n prime. We also have the additional revised E chi prime, where compared to the original one. And now the VOX0 here is a potential drop across the oxide. Is here. This is a voltage drop. VOX0 is a potential drop across oxide for zero applied gate voltage, and it's not necessarily zero because of difference between the phi n and also the electron affinity. And one thing I want to mention is that you will see even under the zero gate bias case, the band is not flat. So that means in the case with MOS, even without any gate bias, the band is not flat. There's already some service charge are already existed. So now we have the this one is already phi n prime as a modified Winkel work function, and this one is a modified electron affinity. And with considering this and this, so we can have following calculation where E phi n plus E VOX0, this plus this is equal to E electron affinity EG over 2 minus E phi S0 plus E phi FP. So this plus this will be equal to this one plus the half of the band diagram, but minus this one, and again to plus this one. So it's not very straightforward, but if you try to calm down to think about this, in the end it still quite makes sense. But in anyhow, just try to find a way this one will be equal to this plus this minus this and plus this. And then we now try to subtract electron affinity. Here. Then we will start to get the modify. So now we have everything in the case with the modify. So that's a E phi plum plus a E VOX0 is equal to E chi plum plus EG over 2 minus E phi S0 plus E phi FP here. So now we rearrange this equation, then we can have the phi S0 plus VOX0 is equal to phi M plum minus this one and then we define this as a phi NS, which is a metal-semiconductor water function difference. So finally, we have the equation to describe the difference between the semiconductor and metal work function difference, which we express as a phi NS here. So the same, we can do exactly the same from the N-type semiconductor. Then we get the same equation. So that's the difference if we have the because in anyhow the metal work function in the semiconductor and metal is always the difference. So we have an equation to estimate this difference. Then we would like to discuss the one particular case is that we consider as a degenerate doped polysilicon. So the purpose is that when we consider the MOS structure, there is a very crucial, is related to the gate electrode. And we have two ways to make the gate electrode. One is use a very highly doped polysilicon, which is N plus or P plus polysilicon. Or we use a metal gate. So, and then if we use a highly doped polysilicon, actually we can consider this as a degenerated doped polysilicon. So we often use this deposit on the outside and use a metal gate, but that's nowadays limited to the certain semiconductor, because for most of the case we would prefer to use metal, but sometimes we should use polysilicon, because polysilicon is the process that has easily fabricate, and then but with a certain consideration we will just use a pure metal gate here. So once we use a doped polysilicon, then this is a semiconductor. So you can see this is a polysilicon semiconductor, but so we still have the EV and EC, but now just our Fermi level will be aligned with our conduction band, or our Fermi level will be aligned with our valence band. So again, we come back for the concept related to our flat band voltage, which you already mentioned in the beginning. Now it's getting more precisely to determine the flat band voltage. So the flat band voltage is defined as an applied gate voltage such that there's no band bending in the semiconductor, and as a result there's no band bending, implies that there is a zero net space charge. In this region. So you can see this is a band diagram under the flat band voltage. So with bias with this one, which we call as a flat band voltage, then we can see there's no band bending. And that means this is a zero net space charge. So, if a gate voltage applied, the potential drop across the outside surface potential will change, and therefore the VG is equal to the additional bias in the outside plus the additional bias in the surface, where we can both consider VOX0 and phi S0, where this is our phi NS. So therefore we can have the VG is equal to VOX plus phi S plus phi NS. And because now we consider the zero net charge in the semiconductor, so therefore with the same charge distribution that this one is a QM plane, and also we assume there is a equilibrium surface charge in the oxide, which is QSS plane. This is assumed an equilibrium fixed surface charge in the oxide. So this is consider this is a metal oxide and P sub. Because right now is zero net charge in the semiconductor, and therefore the QM plane plus the QSS plane should be equal to 0. This plus this should be equal to 0. And also we can consider the VOX will be equal to the oxide electric field will be equal to this QM plane is the bias we apply on the gate side over our Cox, and therefore we can have this Vox is equal to minus QSS over Cox, which is this one. And then under the flat band condition, the surface potential is 0, or phi s is equal to 0. So in this case, this is equal to 0, and this is equal to minus QSS plane over Cox. So therefore, the VFB is equal to phi ns minus QSS plane over Cox. Which is related to our metal wall function with also the surface charge, fixed surface charge in the oxide interface here. The calculation here is not that very straightforward, but in the end just try to want to make sure that the flat band voltage can be correlated with our metal semiconductor wall function and also the QSS, because here we assume that there's a equilibrium fixed surface charge that can balance for our the charge on the metal side in the end create a 0 net charge. Because if we don't have this one, then that means that we definitely will have a certain charge in the P sub. But if once we have a certain charge in the P sub, that will cause a band bending. So we don't want to have a band bending. So it must be some kind of a charge here should be balanced with each one. So that's why we assume there's a QSS plane. So in the end, the formula for the flat band voltage is related to our metal semiconductor wall function difference and also this surface charge. So that's the conclusions here. So the threshold voltage is defined as the applied voltage that required to achieve the threshold inversion point. So assume there's an equilibrium oxide charge QSS and also the positive charge on the metal gate at the threshold voltage is a QM prime T prime. So therefore the charge distributions between the metal and oxide and P sub, this is a metal oxide P substrate here. So now we assume there is a surface charge QSS prime. But now we also assume there's a positive charge on the metal, where is QMT prime, because we apply the positive bias on the metal side, so we can assume there's a positive charge on the metal. And in the end, this should be equal to the inverting charge QSD here. Where this is our XD, and the total charge here, where we define as a Q prime SD maximum. Because now we consider at the threshold point, so that means first the depletion width will reach the maximum. Once it reaches maxima, then all of the charge will become inverted in the channel. So that's why we consider this condition as a QSD at the maxima. So therefore, the QMT prime plus the QSS prime should be equal to this condition. And we also already knew that the QSD prime at the max depletion width is equal to because now we are trying to look at for the boundary between the depletion and also the inversion. So therefore we will consider the boundary will be the maximum depletion width, and beyond this depletion width we'll start to have the inversion charge formation. So we will use this maximum depletion width as a boundary to in the end to calculate for our threshold voltage. So now the next step is that our gate bias can be divided by two considerations. One is the voltage drop in the oxide and voltage drop in the semiconductor that will become our surface potential. But also we can consider the phi s plus the phi ns as well. So the Vg is divided by two parts. One is a voltage drop in oxide, and this one is a voltage drop in the surface. So at the threshold hole, we can define our Vg is equal to Vtn, where Vtn is threshold voltage that creates the electron inversion layer charge. So at this condition, our Vtn, this is a voltage at the threshold hole. So we now replace Vg equal to Tn. That will be equal to Vx T plus the phi s now become the 2 phi fp, which we already mentioned. This is our threshold condition that phi s will become 2 phi fp, and then we have a phi n s here. So basically we just put what we already have in the previous line and then in this equation. So the voltage Vxt can be related to charge on the metal and to the oxide capacitance. So in the end will be calculated as shown here. And with considering the several rewritten, this one will become this one. And most importantly is become the equation shown here, where finally we can include the flat band voltage inside this equation. So again, the whole logic is that why we mentioned to spend effort in the phi is because we want to have the flat band voltage in the end is correlate with the phi s. But why we need to have a flat band voltage? Because in the end because when the people try to develop this equation, this is now we are standing in the position that everyone is unknown. So get to state by state to the end. But actually, when people try to develop this equation, with a certain time, they already have the feeling that threshold voltage should be correlated with the flat band voltage. Threshold voltage should be correlated with the metal-semiconductor work function, because this is accumulation of the lots of people's experience and knowledge. So now we try to correlate the threshold voltage with the flat band. In the end, will become the equation as shown here. Finally, this is the equation that more easily for us to estimate the threshold voltage. So this is a threshold voltage analysis coming from the MOS capacitance. Now we will move on to the next very crucial one, is to have the CV characteristic in the MOS capacitance. That's what we call as a capacitance voltage characteristic. We actually already mentioned this in the Schottky junction. In the junction as well, there's a junction capacitance, and for sure we will be interested to understand the CV in the MOS capacitance as well. So the first case where we discuss is the accumulation mode, which we apply the negative bias. And in this case, if you try to plot the charge distribution between the metal, oxide, and P sub. So because now we apply negative gate bias, so we can have the negative charge accumulate here. And to reach the charge balance, for sure, we can expect there's a positive charge will be a formation on the substrate. So then, and then because of this, also when we consider the capacitance, is actually we consider we apply the DC, where is we apply the constant DC here, but also in the meantime we will apply the AC signal, which we have this AC signal, and this AC signal will create in the sun region. This AC signal will create in the sun region, where this one is a region that the V plus dV, and also this region is V minus dV. So this creates this dq between this AC signal here. So this dq should also reflect on our charge distribution, where sometimes we have the dq as shown here. And this dq prime will also reflect the dq prime at this point. So therefore, we can see with this dq prime and this dq prime, in the end will form the capacitance in between, where this is exactly equal to our oxide capacitance, because this is oxide thickness, this is oxide dielectric constant X zone X. So then we can foresee under the negative bias in the CV, we have the constant C value, C accumulation, which is exactly equal to Cx is exactly equal to X zone X over Tx. So that's the first step, that is the capacitance in the accumulation mode, and then we can estimate the accumulation capacitance. Okay, so now we will start to increase the bias. We will start to move to the next one, that we give the small bias, small positive bias. So in this case, as the same analysis that we were starting from this charge distribution in the case of a metal oxide and P substrate, and the same analysis now we have the positive Q on the metal side, and for sure we will start to form the negative space charge in the substrate with the space charge width of x dt here. And also now we apply the AC signal, and therefore this has additional dq plane, and this dq plane will reflect on the end of our space charge region, which is this part. So now the capacitance is different from the accumulation mode, because now we have to consider the capacitance, which is the oxide capacitance. Also, this space charge region capacitance in series with these two, where Cox and CSD plane here. So now, in the case of the depletion mode, we have the total capacitance 1 over C depletion is equal to 1 over C ox in series with 1 over C space charge region. So in the end, because this is capacitance in series, so the capacitance in series in the end will reduce the capacitance value. Therefore, we can foresee in the previous bias give us a accumulation CACC, but now because of we have a two capacitance in series, and also this capacitance is correlate with our depletion width, and the depletion width with a certain point will reach the maxima, where x dt. So the maxima of the depletion width in the in this depletion capacitance in the end will cause that this total capacitance will reach the minimum value. So the C minima is happen at the max depletion width. So therefore, we can expect as we start to increase the bias with a certain point, with a small positive bias, our depletion region, our depletion capacitance is decreased, and in the end to decrease down to the C min here. So that's the second part for the depletion mode here. So now the next one is we will start to apply enough large gate bias. So now we have a large gate bias. So large gate bias apply. So we consider this large gate bias. Again, we use this charge distribution in the metal, oxide, and P sub. So now we apply the large positive gate bias the same. That means we will have the large positive charge in the gate metal. And also, now we have to consider, first of all, we just finished the depletion region, and then the charge for the negative charge in the depletion region just achieved the maximum depletion width. So the further increase of the gate voltage will not reflect the extension of this depletion region anymore. But however, right now, the further increase of our gate voltage will reflect on this service charge, which is due to inversion electrons here. So again, we have this dq, where we have the dq plug here, and this additional AC induced dq will cause the additional inversion charge in the channel, and therefore this dq plug will exist in the channel rather than in the end of the depletion width here. So these are very consistent with what we understood, that in the case with enough gate bias, our fermion level is close to the conduction band. That means this is a moment we start to generate the service electron. We start to invert the electron in the channel. So this happen in the channel, in the service, is consistent with this band diagram as well. And now if we look at for the capacitance will be formed between this dq and this dq. So in the end, the capacitance under the inversion mode is equal to Cox again. So now we can complete the CV characteristic with the 3 different operation bias. The first one is under the negative bias, that we will form the accumulation capacitance. And then once we start to gradually increase, we can start to see the this is just for the illustration understanding. So that would be once we beyond the certain value, for example the flat band voltage here, we can start to see the voltage decrease, capacitance decrease, and reach to the C mean, where this is our depletion capacitance. But afterwards, because right now we will start to have this dq plug here and dq plug here. So under the very strong large gate bias, that can cause a high inversion electron in this place. So that means the inversion capacitance should be the same like the accumulation. But this is the case of the strong inversion. There's a transition between the depletion and the strong inversion. It's we call as a weak inversion. And in this case, the weak inversion, we will see the increase of the capacitance from the C depletion to the C inversion. Finally, this is a full picture for these three modes. So if you can really understand this C accumulation, C depletion, C inversion, basically you understand everything what we have been lectured regarding for the inversion electron, for the capacitance, and how in the end to form the channel. So the idea low frequency CV with a case of a p-type substrate is here. So this is a capacitance versus voltage, and first of all we have the accumulation, and then this is our accumulation region. Which is equal to Cox, and then after one particular point, which is flat band voltage, and this is a flat band capacitance, then we can start to see the capacitance decrease and reach to the minima here. And then beyond this minima, we can see the capacitance increase again and reach the inversion. So this is a Cox, a gap, and this one is a strong inversion. And this one is weak inversion. And also we have this region is depletion region. And this formula is described for the flat band condition that under the flat band voltage. And this is a case for the idea under the low frequency. But however, if we go to the high frequency, then the CV characteristic will slightly change. So then we have to consider the frequency effects here. There are two sources of electrons that can change the charge density of the inversion layer. Diffusion of minority carrier electron from the p-type substrate across the space charge region, a thermal generation electron hole pair with the space charge region. Both of these processes generate electrons at a particular rate. The electron concentration in the inversion layer cannot change immediately. So that means in the case of the high frequency, the inversion layer charge will not respond to a different charge in the capacitance value. So that means the decoupling here cannot reflect at this region. This is not possible. at the case of the higher frequency. At the higher frequency, the differential change in the charge occurs at the metal in the space charge width in the semiconductor. Therefore, at the high frequency, this will reflect at the space charge region. This is at a high frequency. So this will change our CV characteristic. And therefore, in the case of the high frequency, now we can consider the capacitance is in series with Cox. Also, CSD here. So therefore, the 1/C inversion at the high frequency now becomes 1/Cox in series with 1/CSD. So the CV characteristic original at the low frequency will have this kind of a curve. This is a case of a low frequency. But now, at the high frequency, at the inversion bias, we actually won't get the same as the Cox. It's actually as a Cox in series with a depletion. So therefore, this will become in here as a high frequency. So that's our frequency effects. Also, the CV characteristic can be influenced by the fixed oxide and interface charge as well. This is because of flat band voltage as shown here, which is related to the minus QSS prime over Cox. So if our QSS prime is increased, then we can foresee that our flat band voltage will shift to the left, to a negative. So the flat band voltage shift to more negative voltage for a positive. Oxide charge. The CV characteristic can be used to determine equilibrium fixed oxide charge. So the powerful for CV is we can also use the CV to determine this fixed oxide charge. And also, one thing that we previously mentioned that the capacitance here is equal to the oxide capacitance. So we can use the CV to determine the oxide capacitance. In the end, we can use the CV to determine the oxide thickness, which is very important because in the real fabrication, you probably will try to set the target of our oxide thickness as, for example, 10 nanometer, but you don't know whether it is really 10 nanometer or not. Of course, you can use some material analysis like the SEM, but actually it's very expensive and time consuming. But now if you just quick measure the CV on your fabricate device and bias your CV in the inversion mode, then you can easily to get a simple calculation of your oxide thickness. And this method is widely used in the semiconductor industry nowadays, even for the future. Also, we can use the CV as I mentioned to estimate the fixed oxide charge. And also the next one, we will be interested to look at how the CV, how this the interface charge effect will influence our CV characteristic. So the right hand side is a energy band diagram where we have the conduction band and valence band, and then in the middle we have the intrinsic Fermi energy here. And because of the periodic nature of semiconductor is abruptly terminating at the interface, so allow electronic energy level will exist with the forbidden band gap. This is a similar concept we have mentioned in the when we talk about metal semiconductor interface. We also have been already mentioned that this is our silicon, and then at this interface the silicon surface will be terminated, and once terminated we can foresee that there will be lots of allowed energy state here in this interface. So this allowed energy state is we so-called the interface state. And therefore, we can foresee that once if we have the certain, no matter for the electron or holes, for example, under the positive bias, we might start to form the electrons in the surface, in the channel. But now we have this allowed energy state, so the electrons can start to being located, being jumped into this allowed interface state. So the charge can flow between a semiconductor and interface state, and this will cause the issue of electron trapping. So that's very famous for the trapping effects here. So this will cause a series of reliability issues. So that's very important. This is in here we won't talk too much reliability. In my another course related to reliability and value, we will have the dedicated whole semester to discuss all kind of reliability challenges in the semiconductor device here. So the same, if we have the holes formation in this region, we might also have the same. The hole can be flowed into this interface state, in the end cause the hole trapping. So that's the main issue for the interface charge effects. Okay, so I will stop here because of the next one is a little bit complicated. It needs taking some time to have a further discuss. So let's just stop here and then see you on the Wednesday evening.